Lipids are naturally occurring compounds that are soluble in nonpolar solvents. So the term lipid is actually a very broad term for classes of molecules that are hydrophobic. Now we have two main types of lipids. We have complex lipids, that readily undergo hydrolysis in either basic or acidic conditions, and these can produce smaller fragments, so these can be broken down. Simple liquids do not undergo hydrolysis. So our lipid subcategories have structural similarities, which we'll see in a little bit. So our complex lipids, which we know can be hydrolyzed, include waxes, triglycerides, and phospholipids. Simple lipids, which cannot be hydrolyzed, include steroids, prostaglandins, and terpenes. So these are just some examples of complex lipids. So for waxes, this is an example of spermaceti wax. We have triglycerides, so this is trimyristin. Then we have phospholipids, such as lecithin. So all of these have similar structures where they contain long alkyl chains. So this is part of what makes them so hydrophobic. But these ones also contain ester functional groups. So we're going to focus a lot on triglycerides in this video. Our simple lipids, such as cholesterol, limonene, and PGF, which is a prostaglandin, also have similar structures. So many simple lipids contain rings. So we see the rings here. Several of them contain hydroxyl groups. So those are common features as well as double bonds. Triesters are formed from glycerol, which is this triol here, and long-chain carboxylic acids, which are known as fatty acids. So even though they contain a carboxylic acid functional group, their super long chain of carbons and hydrogens makes them extremely hydrophobic. Now ultimately they will come together to form three ester functional groups and link all three of these together. So this as a whole is known as a triglyceride. Now triglycerides are generally used for long-term energy storage. They can store up to 9 calories per gram, versus carbohydrates and proteins can only store about 4 calories per gram. In order to make the fatty acids hydrophobic or nonpolar, they need to contain a significant number of hydrocarbons. So the fatty acids typically have 12 to 20 carbons in length, and they can be saturated, which means there's no double bonds present in the carbon chain, or they can be what's known as unsaturated, which means they have the presence of a double bond. It could be one or more double bonds, and they're typically in the cis configuration. So stearic acid is an example of a saturated fatty acid, whereas oleic acid is an example of an unsaturated fatty acid. Ultimately, the shape of the fatty acid can impact its melting point. So for linear side chains, such as those in saturated fatty acids, these are able to pack a lot more closely and interact via London dispersion forces. As a result, saturated fatty acids tend to have higher melting points. So for example, myristic acid, which has 14 carbons, has no double bonds present, which means all 14 of these carbons can interact with the 14 carbons of several other molecules and pack very tightly. So myristic acid has a melting point of 54 degrees Celsius. That means at room temperature, this is a solid. Stearic acid, which has even more carbons for a total of 18, has an even higher melting point of 69 degrees Celsius. That's because this longer chain means more London dispersion force interactions, which is going to increase the melting point. Now, if we compare that to palmitoleic acid, which is unsaturated and contains a cis double bond here, this cis double bond introduces a kink into the chain and decreases the amount of interaction that this chain can have with other chains. So as a result, the melting point of this molecule is 0 degrees Celsius. So that means at room temperature, which is around 25 degrees Celsius, this is actually going to be in a liquid form. It needs to get all the way down to 0 degrees Celsius before this turns into a solid. So the trend is that saturated fatty acids have higher melting points than unsaturated fatty acids. And the higher molecular weight the fatty acid is, or the more carbons it has, the higher the melting point. And that's because just simply an increase in the intermolecular forces. We see the same trends for the triglycerides, which contain 3 of the fatty acid chains. By definition, fats are triglycerides that are solids at room temperature, and fats have a higher number of saturated fatty acids in their chains. Oils, on the other hand, are triglycerides that are liquid at room temperature, and oils for the most part contain a larger number of unsaturated chains. So for instance, this tristerin here, we can see these chains as long, meaning there's no presence of double bonds that introduce that kink. So these can pack very tightly together, which is why we see such a high melting point of 72 degrees Celsius. For this one here, we can see that these fatty acid chains do contain these kinks, which means they have the presence of the cis double bond. So as a result, they can't pack as tightly together, and that's why we see a lower melting point. So for instance, butter, which is solid at room temperature, is technically a fat and contains a high amount of saturated fatty acids. Canola oil, which is a liquid, contains a high amount of unsaturated fatty acids, which is why we see it as a liquid. Even under the category of unsaturated fatty acids, there's different types of unsaturated fatty acids. So unsaturated fatty acids are also known as monounsaturated fatty acids. These contain one cis double bond. So an example of that is palmitoleic acid, which has the cis double bond located here. There's also polyunsaturated fatty acids. These contain 2 or more double bonds. And the first usually begins around carbon number 9. And we number the carbons starting with the carbonyl as carbon number 1 and moving our way towards the end of the chain. Now, an example of a polyunsaturated fatty acid is this one, which is linoleic acid. And as we can see, with the introduction of a second double bond, we add an additional kink, which is going to reduce the melting point even more. So the melting point for linoleic acid is -5 degrees Celsius. Now, it's important to note with polyunsaturated fatty acids is they are never conjugated. They are always going to be separated by at least 2 bonds. And finally, we have omega-3 fatty acids. A lot of times these are talked about as being important to eat and found in fish and nuts. So omega-3 fatty acids get their term from having a double bond on the third to last carbon of the chain. So typically, we number the carbons starting with the carbonyl going towards the end. The end of the chain are called the omega carbons. So the double bond that starts on omega 1, 2, 3, which is here, is called an omega-3 fatty acid. Now this fatty acid here, which is DHA, is an important structural component of the brain, skin, and retina and is important for pregnant women. Unsaturated triglycerides can undergo hydrogenation. So we saw with previous reactions that if we have a double bond, we can turn it into single bonds only using hydrogen gas plus a metal catalyst. So we can take an unsaturated fatty acid and hydrogenate it to make it a complete saturated fatty acid. So as a result, hydrogenating unsaturated triglycerides forms saturated triglycerides. Now, the reason that you would perform hydrogenation on an unsaturated fatty acid is because unsaturated fatty acids are actually susceptible to autooxidation. And we talked about this in the radicals chapter. So the hydrogens that are located at the allylic position, so one bond away from the double bond, are fairly acidic and are capable of reacting with free radicals. Now, once a radical forms at either one of these positions, it's stabilized by resonance. Then it can go on to react with oxygen in the air. Ultimately, we will form a hydroperoxide, which essentially ruins the fatty acid chain. Hydrogenation is often used to preserve the shelf life of food products. So essentially, we are preventing autooxidation from occurring. It can also be used to produce a different type of product. However, complete hydrogenation of a triglyceride can often lead to hard or brittle triglycerides, which is not ideal in a manufacturing setting. So, for example, margarine is partially hydrogenated, and margarine specifically is partially hydrogenated vegetable oil. What they do is they take vegetable oil, which is liquid at room temperature, and they hydrogenate it until they get the desired hard consistency that we typically associate with margarine as a butter substitute. Now, with partial hydrogenation, some of the carbon-carbon double bonds are capable of isomerizing from the cis configuration to the trans configuration. And it's this type of process that produces trans fats. Trans fats are not natural. They are the result of partial hydrogenation of fatty acids. As we'll see in lab, triglycerides can undergo hydrolysis to produce soap. Specifically, we're doing ester hydrolysis under basic conditions. So we saw this exact reaction in the carboxylic acids chapter. So these three esters will undergo hydrolysis with excess sodium hydroxide to produce glycerol plus 3 carboxylate ions. These carboxylate ions are the components of soap. The way that soap works is it contains a nonpolar hydrophobic group which will interact with dirt and grime, which tends to be nonpolar molecules. The polar group is free to interact with water molecules. So what happens is these molecules can end up forming micelles around nonpolar particles. On the outside of the micelles are going to be the polar heads, which can allow the micelle to interact with water and be rinsed off. The next class of lipids we'll talk about are steroids. Steroids mainly function as chemical messengers, and all steroids have this tetracyclic skeleton, which is known as the ABCD ring system. So for every steroid, it consists of 1, 2, 3 6-membered rings that are fused together in this form, as well as 1 5-membered ring, for a total of 17 carbons in this basic skeleton. Now, if we consider all of these rings in their true three-dimensional forms, we know that cyclohexane rings form chair structures. So we can actually draw that out. So we have 3 chairs that are fused together, and then the 5-membered ring forms a boat structure. Now, steroids are very rigid. They're stuck in this form. The trans ring fusions prevent any ring flipping from occurring, so it really means that this is a rigid, stuck form of a steroid molecule. So cholesterol is an example of a steroid. Now, cholesterol is rigid and it allows it to act as a stiffening agent for cell membranes, so it is very important to biological systems. So this is our structure of cholesterol, and this is it drawn out in the atoms and bonds. Now I want to point out 2 methyl groups, and these are the methyl groups between rings A and B and rings C and D. These are known as the angular methyl groups. Now these groups are important because they help determine the stereochemistry of the other substituents on the cholesterol skeleton. Now if the substituents are on the same side as the angular methyl groups, those are known as beta substituents. If they're on the opposite side, they're known as alpha substituents. So for instance, this OH group, which can be considered a substituent off of the main skeleton, is on the same side as the angular methyl groups, which would make it a beta substituent. Now this group over here, this alkyl group, is known as the side chain, which hangs off of the main skeleton of the cholesterol molecule. Now some interesting facts about cholesterol. Cholesterol is the most widely occurring steroid. It has 8 chiral centers. So depending on the number of chiral centers, we can actually predict the number of possible stereoisomers that can exist for a molecule. We use the simple formula of 2 to the power of the number of chiral centers, which means cholesterol itself has 256 possible stereoisomers. But it's important to note that out of those 256 stereoisomers, only one of them is cholesterol and has the function of cholesterol, and that is the figure that we see here. So any of the other stereoisomers of cholesterol would have different functions or no function at all. Sex hormones are also steroids, and here's an example of a bunch of different sex hormones, including testosterone, estradiol, progesterone. Again, these all have the same basic structure of the 6-membered rings fused with the 5-membered rings as well. Adrenocorticohormones are also steroids, including cortisone and cortisol. Now, these molecules are used therapeutically to prevent inflammation and treat skin conditions. So these are widely used in pharmaceuticals. And the last class of lipids that we'll talk about are the terpenes. Terpenes are a widely diverse group of compounds. And what the interesting thing about terpenes is they're all assembled from isoprene units. So this is an isoprene molecule here. An isoprene unit is simply redrawing the molecule without the double bonds. So an isoprene unit consists of 5 carbons, and specifically it's going to be 1, 2, 3, 4 carbons connected in a row, and then 1 methyl group connected to the second carbon. So we have this kind of Y shape. Now, in order for a molecule to be classified as a terpene, the number of carbon atoms in the molecule must be a multiple of 5. And we'll see how different molecules are assembled in these isoprene units. So these are several examples of terpenes. In all 3 of these molecules, the carbon atoms are in multiples of 5, and we can identify the isoprene units by outlining them. So in our first molecule, we have 10 carbon atoms, which means it's made up of 2 isoprene units. So we've circled one here. So again, we have the 1, 2, 3, 4 carbons in a row, and the methyl group connected to the second carbon. Then over here, we have 1, 2, 3, 4 carbons in a row, and again, a carbon connected to the second carbon. So we can ignore any of the double bonds. We're just focusing on the number of carbons and making sure they're connected in the correct way. Over here, we have another 10 carbon molecule. And again, we have 1, 2, 3, 4 carbons with a carbon connected to the second. And then we have a total of 1, 2, 3, 4, and then a single carbon connected to the second. So terpenes can even be incorporated into rings. Now, when we're identifying the isoprene units, we never double count a carbon. So all carbon atoms should be accounted for in these specific isoprene units. Over here, we have a 15 carbon atom molecule, which means it's made up of 3 isoprene units, and they're all shown outlined here. So many terpenes are isolated from plant oils, which means they have strong fragrances, and they're often used as flavorants or odorants. So these are some examples of some terpenes that are familiar to us. We synthesized menthol in Chem 226. One of our virtual labs was on camphor, so that's a terpene as well. Then there's also R-carvone, which we didn't do a lab on, but in previous years we have examined carvones and how the different enantiomers have different scents. So let's go ahead and determine the isoprene units in all of these molecules. So again, we want to identify 4 carbons in a row plus a methyl group attached to the second carbon. So we can go ahead and start here. We have 1, 2, 3, 4 carbons and a carbon connected to the second. So we'll go ahead and outline that. We can ignore any OHs. They're not a part of the isoprene unit. Then we have 1, 2, 3, 4 carbons in a row with a carbon connected to the second. Sometimes there's multiple ways to identify the isoprene units, but we just want to make sure all of the carbons are accounted for. With camphor, we have 1, 2, 3, 4 carbons with the methyl group attached to the second. And then 1, 2, 3, 4, again with a carbon attached to the second. With our carvone, 1, 2, 3, 4, the carbon attached to the second. And 1, 2, 3, 4 with the carbon attached to the second. So each of these molecules is made up of 2 isoprene units. So terpenes are classified by the number of carbon atoms they have. So the simplest terpene is typically a monoterpene, and that consists of 10 carbon atoms or 2 isoprene units. We also have sesquiterpenes, which are made up of 15 carbon atoms or 3 isoprene units. There's diterpenes, which are consisting of 20 carbons as well as 4 isoprene units. Triterpene with 30 carbons and 6 isoprene units, or tetraterpenes with 40 carbons and 8 isoprene units. So beta-carotene, which we saw a lot on the conjugated systems chapter, is actually a terpene, and it is made up of 8 isoprene units, so that makes it a tetraterpene. It has a total of 40 carbons involved. And this structure shows all of the isoprene units making up our beta-carotene.